In today's class, we are going to discuss about the topic called center of gravity. So what is center of gravity? The center of gravity of a body is the point about which the algebraic sum of moments of weights of all the particles constituting the body is zero. Okay, this is the definition for center of gravity. What happens at the center of gravity is that when we take the whole weight of a body, the point where the center of gravity is, we can hold that object by just holding at that point. Okay, let's take some examples. First of all, let's consider a rod. So if we say, or if we talk about a rod, what happens is we can hold this rod by just keeping our finger in this middle point. So we can hold the rod. So this middle point of this rod is basically the center of gravity, denoted by capital G. So how can we relate with the definition over here? The center of gravity of a body is the point about which the algebraic sum of moment of weights. Now this rod is made up of many particles. Say some particles are over here. So particles that are present over here, because of this there will be anti-clockwise moment. Particles over here, because of their weight, there will be clockwise moment. Now what happens is, in the algebraic sum of the anti-clockwise and the clockwise, they are equal. So the algebraic sum of the moment of force of all the particles constituting the body is zero. How much ever anti-clockwise is there, that much clockwise is there. So when we add them, what happens is clockwise and anti-clockwise, they cancel off each other, and the algebraic sum of moment of weights become zero. So this is what the center of gravity is. So for a rod, the center of gravity is at the midpoint of the rod. Number 2, circular ring. So for a circular ring, the center of gravity is in the center of this ring. Over here, we need to remember that this is a ring. So this space is empty, and this center of gravity does not lie on the object. It lies outside the object. This is an empty space over here. So center of gravity need not be on the object. It can be outside the object as well. Okay, so this is at the geometric center. Number third, circular disc. Now when we talk about a disc, this disc means there is material over here. So when considering a disc, the center of gravity lies in the disc itself, that is, it is within the material. But when we consider a ring, this whole space inside this is empty. So this is not in the material, this is not within the material. So center of gravity need not always lie in the material. It may sometimes lie in material, it may sometimes lie outside the material. This is also the geometric center. Number 4 is a hollow or solid sphere. Sphere basically denotes a ball. This is a circle that is filled. So this is a disc. Disc as in, say, the compact disc that we use, CDs that we say, are examples of disc. This ring example, we can take the rings that we wear in the hand, fingers. So that is example of ring. Or the bangles are basically the shape of rings, where inside it is hollow. Disc becomes the CD that we use, that is a disc, and a solid or hollow sphere is basically a ball that we use. So I'm not making the shape for a ball. It will be basically, while making in a notebook, I'll make it circular itself. But actually when you visualize it, visualize a ball. So at the center of the ball, there will lie the center of gravity. So that will lie on the geometric center of the sphere. That is at the center of a ball. Number 5th, a solid cone. Solid basically means it is completely filled, like a rod is a solid one, but when we say a pipe, it is a hollow object. So solid cone, the center of gravity lies at the at a height h/4 from the base on its axis. Number 6, hollow cone. At a height h/3 from the base on its axis. Okay, a cone looks like this. And if we take the center of the circle that is present at the bottom, and if we take this top point and when we join this, this is called the axis of the cone, and this is the height of the cone. So we are taking h/4 from the base in case of a solid cone and h/3 from the base of a hollow cone. So this will be the point for h/4, because h/4 is less than h/3 and h/3 will be somewhere over here. So these are the center of gravities of a solid or a hollow cone. Number 7. Triangular lamina or scalene triangle. So for a triangular lamina or a scalene triangle, say we take a triangle at random. So if we take the median is basically from a vertex on the opposite side, the midpoint. If we join this is called the median. From here again, this one we join, we call it median. From this one again we join midpoint to the vertex, we get a median. So the intersection of the medians, this forms the center of gravity for a scalene triangle or any triangle for that case. So triangular lamina is the point of intersection of the medians. Number 8. Solid or hollow cylinder. For a cylinder, like we considered the axis of a cone, we'll also consider an axis of the cylinder. So we take the center of the upper circle, center of the lower circle, and we join this centers. So this line that we get over here is called the axis. And for a cylinder, the center of gravity lies at the center of this axis. So solid or hollow cylinder, it lies at the midpoint on the axis of cylinder. And number 9, parallelogram or a rectangular lamina. Square or rhombus. In all these cases, what will happen is the center of gravity will lie at the point of intersection of the diagonals. So say a parallelogram. So one of the diagonal, another diagonal. So the point of intersection is the center of gravity. See a rectangular lamina, basically a rectangle if we take. So this diagonals we take, and the intersection of diagonals form the center of gravity. Case of a square, again what we do is we make the diagonals, the point of intersection of the diagonals form the center of gravity. And for a rhombus as well, we take the point of intersection of its diagonals. So this point of intersection forms the center of gravity. Okay, so these are the center of gravity of some common regular objects. Now we'll see how to determine the center of gravity of an irregular lamina by the method of balance using a plumb line. Okay. This may sound quite difficult, but is actually quite easy. Say we have an irregular lamina. Okay. Now, let this irregular lamina be A. So let A be an irregular lamina. As shown in the alongside figure. For which the position of center of gravity is to be determined. Now what we do is we make 3 fine holes at A, B, C near the edge of the lamina. So say this is hole A, hole B and hole C. So we made 3 holes A, B and C near the edge of the lamina. Now suspend the given lamina along with a plumb line from the hole A on a pin clamped horizontally on a retort stand. Okay, what we are doing basically over here is that we are taking from a hole, we are taking a plumb line and we are seeing where, if we take this line, is this lamina stable. So we find that when we get a line like this, then what happens is this balance out each other. The left hand side and the right hand side, they balance out each other and this body becomes stable. So this line is a line where this body gets stable. So check that the lamina is free to oscillate on the nail about the point of suspension. When the lamina has come to rest, draw a straight line AD along the plumb line. So what we did is through A we took a plumb line passing through the hole A and we checked at which line like this was this body stable. So the irregular lamina was found to be stable at around this line. So what we do is we make a line AD along this plumb line. This is our line AD. In a similar way, now what we'll do is we'll take from point B and we'll see at which line through which where the plumb line is kept so that his body becomes stable. So from B we see that in this line the upper half and the lower half, the weights they cancel off each other, moment of weights they cancel off each other, and this body becomes stable. So from B we make, say we had A B C D is used, so say we use the alphabet E. So in BE we see that this body becomes stable. And from C, now what we see is again we take C, and through C what we do is we are checking in which line it becomes stable, and we see that through this line it becomes stable. The moment of weights of the upper half and the lower half they cancel off each other and it becomes stable at this point. Say we name this as CF. So what we are doing is we are repeating the procedure. So repeat the procedure. By suspending the lamina through the hole B and then through the hole C. For which we get straight lines BE and CF. BE and CF respectively. It is noticed that lines AD, BE and CF intersect each other at a common point say we name this common point as capital G. So this common point we name this as capital G, which is the position of center of gravity of the lamina. Now you can hold this object, irregular lamina. We did not know the center of gravity earlier, but now for this irregular lamina, if we place a knife edge in this way and if we try to hold it upside down, say this is an irregular lamina, and if we try to hold it by holding it at point G, this will become stable. So we found the center of gravity by making 3 holes, and through these 3 holes one by one we took the plumb lines and we saw about which line this body got stable. So from AD it was stable, next at BE this was stable, and finally at CF it was stable. So all these 3 lines we saw that intersect at one point, that is called G, and this G marks the position of the center of gravity in the lamina. So this is how we find the center of gravity of an irregular lamina by the method of balance using a plumb line. Okay, this language that I have used here, this you need not copy exactly same. You can write it in your own way and you can show it to me. I'll check it for you. Okay. Some notes for center of gravity. Point 1. The position of the center of gravity of a body of a given mass depends upon its shape. We already showed that depending upon the shape, the center of gravity lies at different points in an object. Second, it is not necessary that the center of gravity always be within the material of the body. So for this we can take a number of examples. Say a circular ring. In case of a ring, think of a bangle. So the center of gravity is at the center, but this center is not within the material. You can take example of a hollow sphere, not the solid sphere, a hollow sphere. Hollow sphere is empty from the inside. So at the center of that sphere will lie the center of gravity, but the center is not a material, is not within the material. Solid cone, not solid cone, hollow cone. Hollow cone is also empty on the inside. For a hollow cone as well, it will not lie within the material. Then you can take example of hollow cylinder as well. For a hollow cylinder as well, this is empty on the inside, just like a pipe. So this point center of gravity will not lie at the within the material of the body. Okay, and the third point, by the concept of center of gravity, a body of weight W can be considered as a point particle of a weight W at its center of gravity. So basically what we are doing, center of gravity. So basically what we are doing by finding the center of gravity is that we are considering the whole body acting, whole mass of the body acting at one single point. So we can consider the whole body as just one point where the whole weight of the body acts at this point. So this is also another importance of center of gravity. We can consider huge objects as just a point object with the help of center of gravity. Okay, so with this center of gravity is over. The next topic that we are going to discuss is the uniform circular motion. So uniform circular motion is very important. So what is uniform circular motion? When a particle moves with a constant speed in a circular path, its motion is said to be uniform circular motion. Okay. So when a body moves in a circle like this, say if a body is at point A, so the direction that it is moving is in this. So it moves in this direction. So it turns like this. Say when it reaches a point B, it now moves in this direction. So at every point what is happening is the body is changing its direction. Say at point C, now it moves in this direction. And at point D, it moves in this direction. And what is this direction? Is a tangent. This direction is basically the tangential direction. Tangent is basically a point on the circle where from the radius what happens is this makes an angle of 90 degree. So it only touches the circle at one point. This is called a tangent to the circle. So at any point the direction of motion is along the tangent drawn at the point of at that point of the circular path. This is the direction of the object when it moves in a circle at uniform circular motion. Okay, now in uniform circular motion, what is happening is the body is continuously moving, but the speed is constant. But as the speed is constant, what is happening is direction is changing. Velocity is a vector quantity which deals with the magnitude as well as the direction. So if direction continuously changes, what happens is velocity also changes. That is why when we consider a uniform circular motion, we say that a uniform circular motion is an accelerated motion because there is change in velocity. Okay, so the velocity of the particle in circular motion is variable since its direction is changing at every point or the circular motion is accelerated even though the speed of particle is uniform. So what we conclude from this is that though the body is moving with uniform speed, it is moving with variable velocity as its velocity is changing because of changing direction, and with changing velocity there will be some acceleration because acceleration is change in velocity by time. So as there is acceleration, the body is said to be accelerated. Okay. So what is the difference between uniform circular motion and uniform linear motion? In uniform linear motion, linear means in a straight line. So in a uniform linear motion, what happens is there is no change in direction. So with no change in direction, the velocity is also constant. So in uniform linear motion, the speed and velocity are constant, and acceleration is 0. Since there is no change in velocity, that is velocity is constant, so acceleration is 0. that is uniform linear motion is an unaccelerated motion. While in a uniform circular motion, the velocity is variable even though the speed is constant. So it is an accelerated motion. Since velocity is changing, so it will become an accelerated motion. So this is our main difference between uniform circular motion and uniform linear motion. Okay. Now the last topic in the chapter that we are going to deal with under the uniform circular motion is the centripetal and centrifugal force. So first we are going to see what centripetal force is. The force acting on a body moving in a circular path in the direction towards the center of the circular path. This is the centripetal force, the force that acts towards the center. Centri meaning center, petal means seeking. So the center seeking or the force that acts towards the center is called the centripetal force. Examples. Number 1. In an atom, an electron moves around the nucleus in a circular path for which the required centripetal force is obtained from electrostatic force of attraction on the negatively charged electron by the positively charged nucleus. So basically what happens is, we know that the nucleus has protons and neutrons. So the nucleus is positively charged and electrons that move around the nucleus is negatively charged. So the positive and the negative, they attract each other. So this is called the electrostatic force of attraction, because of which we get the required centripetal force. Centripetal force is different in different cases. Like in an atom, an electron and the nucleus, this centripetal force is the electrostatic force of attraction. Say let's take example 2. A planet moves around the sun in an elliptical path for which the gravitational force of attraction on the planet by the sun provides the necessary centripetal force. So when a planet moves around the sun in its path, the sun pulls the planet towards itself by gravitational force, and this gravitational force provides the necessary centripetal force. That is, the planet is attracted towards the center seeking force, the gravitational force in this case provides the centripetal force. Or you can take the example of moon and the earth. So as the moon moves around the earth pulls the moon towards the center, that is towards itself, and this gravitational force of the earth to the moon towards the earth provides the necessary centripetal force. So gravitational force of the moon towards the earth provides the necessary centripetal force in case of moon and earth. Because moon is a smaller object, earth is larger as compared to the moon. So moon is attracted towards the earth by gravitational force. And the last example that we see is when a stone tied at the end of a string is whirled in a circular path holding its other end in the hand So whenever we consider strings like this, what happens is when we rotate the stone tied to the string and we hold the string, so what happens is the string pulls the stone towards the center by the force of tension. So whenever you consider string, the tension in the string provides the centripetal force. And we know that to every action there is an equal and opposite reaction. So when we have a center seeking force, we also have a force that pushes this object away from the center. This force is called the centrifugal force. Centrifugal force is a force assumed by an observer moving with the body to be acting on the body in a direction away from the center of circular path. Okay, let's consider some examples over here. Think of a merry-go-round. Whenever you sit in a merry-go-round, the same like when a stone is tied at the end of a string, what happens is when you sit on a merry-go-round, the tension that is there in the rod that is attached to the center holds and provides the necessary centripetal force. And whenever you are sitting in the merry-go-round, you always feel that you are going to fall outwards. That feeling that you get of going outwards is the centrifugal force. It is assumed by an observer. It is not the real force. It is a fictitious force. That is, it is not real. So, centrifugal force is not a real force. It is a fictitious force. What is a fictitious force? A force which really in the real world does not exist, but is considered to understand a certain motion. Just like when you tie a stone to a thread and you whirl it around, what happens is if you suddenly cut the string, the stone will move away from the center. That movement is described by this centrifugal force. This is not a real force, it is a fictitious force. So a force which really does not exist but is considered. We consider it so that we can understand the motion of that stone which on cutting the thread moves away from the center. So this force is called the centrifugal force. So with this we come to the end of this chapter. Thank you.